Lesson 25, Basic Rules of Probability, Example 14. Based on the results of the Sierra College Elementary Statistics Student Survey, can one conclude that a student's rating of their mathematics ability is made independent of their gender? This question is trying to determine whether these events are independent of one another. Statistically, we define independent events as follows. Events E and F are independent if it can be shown that the probability of E given F is equal to the probability of E without given F, where the symbol E can represent any outcome of one event, and the symbol F can represent any outcome of the other event. So the events we're trying to determine whether they're independent is mathematics ability and gender. Now, mathematics ability wasn't specified exactly which outcome to focus on, so we are free to choose whichever one we want. It could be below average, just average, or above average. So in this example, let's let the E represent a just average mathematics ability rating. Now, for the other event, gender, it's not specified which gender in this problem, male or female, so we're free to choose whichever one we would like to focus on. For the sake of this example, let's let the symbol F represent the gender female. Thus, to answer the question of independence, we're going to focus on this specific probability comparison. Does the probability of a student rating their math ability as just average, given that they're female, equals the probability of being just average without given they're female? This is the question we're trying to answer. Are these two probabilities equal? If they are equal, they're considered to be independent. But if they're not equal, these events are not independent. So first, calculating the probability that the student would rate their math ability as just average, given they're female, is calculated this way. Given the information of being female, redefines the total. So the total that we base this probability on is the given 27 females, of which 17 rated their math ability as just average. So 17 out of the 27 females were just average, works out to be 63.0%. So this value, 63.0%, is compared to the percentage of students who rate their math ability as just average when they're not given the information on gender. So without the given information, the total becomes the total amount in the student survey, which was 44 students. And now the total of 44 students in the survey, 11 plus 17, or 28 of the students, rated their math ability as just average. And the 28 out of 44 works out to be about 63.6%. So now we have the probabilities that we need to make the comparison. Does the 63.0% equal the 63.6%? Now, mathematically speaking, these probabilities are not equal. And when these probabilities are not equal, the events are not independent. But before we reach this conclusion, we need to take into consideration that these results here were not based on a population. It was based off of a student survey or a sample. So these percentages are actually sample proportions, or p-hats. And we know that just due to results of random sampling, the results in the sample aren't necessarily going to give us exactly the results that are in the population. So here are the 63% of students that rate their math ability as just average given they're female. The result means that it's essentially somewhere within a margin of error of 63.0%. And the percentage of students who just rate their mathematics ability as just average out of the total in the survey, 63.6%, is essentially about what it is within a margin of error in the whole population. So looking at them this way, 63.0% is very close to 63.6%. So statistically speaking, these probabilities are close enough to be considered equal. And when these probabilities are considered equal, the events are considered independent. This is the result that seems reasonable to conclude. So, since the probability that a student rates their math ability as just average given they were female is approximately equal to the probability that they were just average, it is reasonable to conclude that a student's rating of their mathematics ability is most likely made independent of their gender. Therefore, we'll answer the question this way. Therefore, based on the results of the Sierra College Elementary Statistics Student Survey, one can conclude that a student's rating of their mathematics ability is made independent of their gender. Now, even though 63.0% does not exactly equal 63.6%, statistical reasoning supports the conclusion that these results were, in essence, close enough to be considered equal. This conclusion can be justified for several reasons. One is that the probabilities used to reach the conclusion were based on the results of a random sample. With random samples, the results can vary within a margin of error due to chance alone. Another is that for certain sample sizes, particular results cannot be mathematically achieved. For instance, in order for the probability of just average to equal exactly 63.0%, when the sample size is 44 students, the number of students that rated their mathematics ability as just average would have to be equal to 27.72. That's because 27.72 divided by 44 exactly equals 63.0%. However, this result cannot be achieved since the number of students is discrete. That is, it's impossible to get 27.72 students to rate their math ability as just average. In the survey, the result would be something more like 28 or 27 students. The solution presented in this example focused on the events just average and female to answer the question of independence. In fact, it does not matter which outcomes are represented by the symbols E and F. The conclusion reached would be the same regardless of the particular events that are analyzed. So, instead, if event E represented the gender male and event F represented a mathematics ability rating of above average, the question of independence would be answered by analyzing the probability of male given above average compared to the probability of male without given above average. If these are equal, the conclusion is they're independent. If these probabilities are not equal, the conclusion is they are not independent. So, focusing on the first one here, what's the probability that a student is male given they rated their mathematics ability as above average? Given the above average redefines the total. So in the survey, there was a total of 8 students who rated their mathematics ability as above average. Of these 8 students, 4 were male. So 4 out of 8 is 50%. This 50% needs to be compared to the percentage of male without given math ability rating. So the percentage of students out of the total survey of 44 students who were male would be the 2 plus 11 plus 4, or 17 males, out of the total of 44 students in the survey. The 17 out of 44 is 38.6%. So now, making the comparison, does the 50% equal the 38.6%? Well, these percentages definitely look different, and we may want to conclude that they're not equal, hence concluding that they are not independent. But looking closer from a statistical reasoning point of view, that 50% was the result of a calculation of 4 out of 8. That is, there were only 8 students who rated their math ability as above average. This is a very small sample size. What if, just by chance, we happen to get 1 fewer male who rated their math ability as above average? In that case, we would have 3 out of 8. And 3 out of 8 is 37.5%, which would be below the 38.6%. So just 1 student difference here can give us a result that was lower than the 38.6% or one that was higher than the 38.6%. In fact, with this sample size of 8 in this group, it would be impossible to get an exactly 38.6%. That is, we usually would get something around the 38.6% if they were equal. And here, the 50 and the 37.5% is as close as this can get based on a sample of 8 above average students to the 38.6%. So statistically speaking, we're going to argue that these probabilities are close enough to be considered equal. And when these probabilities are considered equal, the events are considered independent. So, since the probability of being male given above average is approximately equal to the probability of just being male, it is reasonable to conclude that a student's rating of their mathematics ability is most likely made independent of their gender. Therefore, based on the results of the Sierra College Elementary Statistics Student Survey, one can conclude that a student's rating of their mathematics ability is made independent of their gender. So it appears that gender does not affect the way in which a Sierra College Elementary Statistics student would rate their ability as a mathematics student. That is, the student's responses to the question, how would you rate your ability as a mathematics student, were essentially the same for both males and females. We could see this in the results. The pattern for males, we had 2, 11, and 4, which was low, high, low, essentially bell-shaped. The pattern of responses for female, 6, 17, 4, again was low, high, low, essentially bell-shaped, which is reflected in the overall total for all students, 8, 28, 8, low, high, low, bell-shaped. So basically the pattern response was the same whether you were male or female. So gender seems to not make a difference when it comes to students rating their own mathematics ability. The differences that we see here is pretty much due to chance alone in random sampling. That is, if we were just to happen to have one fewer above average male in the sample and one more below average male in the sample, the pattern would shift to a 3, 11, 3. And for females, if we just happen to get one fewer female who rated their math ability as below average, and instead got one more female who rated their math ability as above average, the pattern would be 5, 17, 5. So really the difference in these results here is just due to one more, one less student in particular categories. And this isn't due to the fact that they're male or female. It's more due to the fact that it was just chance in random sampling.